I'm going to be talking today about the snow mass perspective on Spec S5 because snow mass is, of course, where it got defined. And I'll be talking a little bit about what that process was and what we thought about the experiment. So snow mass is a component of the higher energy physics attempt to prioritize what they're going to do over the next decade or so. It completed in 2022 and is really focused on what are the most important questions in high energy physics that then get synthesized by P5, the Particle Physics Project Prioritization Panel, which turns those ideas of what the interesting science is into how we should prioritize projects. Of course, Spec S5 was favored in that. And so the snow mass process is driven by community input. It's very much things filtering in from the bottom up. So it starts with a set of letters of interest, just a few pages long. For the cosmic frontier alone, there are more than 250 letters of interest. Many of them related to Spec S5, many of them not. And then those got digested into a set of white papers. So there was an attempt to sort of bring people together interested in similar topics. So there's a more limited set of white papers. Those then get digested in a set of panel reports focused on specific topics. I'll talk about some of these panel reports as we go on. That then get summarized into frontier reports that bring together the input from all the different panels in one particular frontier. And for Spec S5, we're interested in what's called the cosmic frontier within high energy physics. And then those reports, there's a whole set of them, 10 of them that got digested in the snow mass report, which, as you can see, there's so many layers of summarization that, what is 10 pages in one of these things may end up being a sentence by the time you're in the snow mass report. And then the snow mass report, along with other input, leads to the P5 report. That again, you're hoping maybe you get a sentence or two in some cases on your particular topic. But a lot of work went in, right? Hundreds and hundreds of people just within the cosmic frontier worked on these letters of interest, the white papers on down. And so the cosmic frontier was well represented in this process. So there were more than 500 white papers within the snow mass process, more than 1,000 letters of interest. So 79 different topical group reports. I'll talk about just a few of those. And 10 frontier summaries, with the cosmic frontier summary being an example. And so I've posted a PDF of my slides, and for everything I'll be talking about, all the reports I've been talking about, I've put in live links. So you can go to the PDF, follow the links for basically all the reports that are relevant for Spec S5. So in the case of the cosmic frontier, we're not talking about, particle detectors, right? So there are only some of the panels that really focused on Spec S5 science. That starts with the panel on cosmic probes of dark matter, which does discuss applications of Spec S5. The bulk of the focus is in the Cosmic Frontier 4 panel, Dark Energy and Cosmic Acceleration, the Modern Universe. As we've heard, the science for Spec S5 goes far beyond dark energy and cosmic acceleration. Nonetheless, most of the focus on Spec S5 was there, and most of this report focuses on Spec S5. It's really the chief recommendation, chief idea that helped organize our thinking. The report on cosmic acceleration at cosmic dawn and before, basically Z greater than 5, still ended up talking about Spec S5 as really the next frontier for studying inflation beyond CMBS4. The CF6 panel, Dave Schlegel was on that, was one of the leaders of that, focused on complementary probes and new facilities, again, talked about what the possibilities were for implementing a Spec S5. And I should note on CF4, I was one of the conveners, but Jim Annis, Anja Slozar, and in the early days, Masao Sako helped organize that effort. And then, hundreds of people across the community contributed. So this is from the SNOMAS Cosmic Frontier Overall Report. Sometimes we call this the waterfall plot. It's showing how for different metrics we care about, the constraints on that metric get better and better over time. So starting with what redshift you can measure dark energy density to 1% of the total density. Scalar to tensor ratio, Spec S5 doesn't matter for FNL, as we've heard about, it's very important. looking for features in the inflationary power spectrum. SPEC-S5 is important for. Gravitational waves, it is not. Constraining the number of effective species in concert with CMBS4 and SPEC-S5, you get the strongest constraints. And trying to figure out the minimum mass of dark matter halos, or studying dark matter halos down to as low a mass as possible. Again, SPEC-S5 can play a key role in. And unfortunately, I don't have time to go into the details of all this, but fortunately, you've got a whole set of reports that lead to a whole set of white papers that give you all the details for anything you're interested in. So in CF4, there were basically 4 of the 6 white papers had a big focus on SPEC-S5. 3 of those were organized by the panel from the letters of interest. One focused on really what a large spectroscopic telescope could do for imaging surveys like Rubin LSST, but also what imaging surveys can do for spectroscopic facilities. One focused on the gains from having high density samples with multiple tracers at relatively low redshifts, below 1 or 1.5. One focused on higher redshift samples, which is the theme of much of the SPEC-S5 science we've been hearing about, and 2 contributed papers, one focused on Rubin Observatory after LSST, which could still be relevant. You could do imaging for target selection for SPEC-S5, and one focused on the megamapper. There were also a couple of white papers from other panels that I've also linked here. And again, these are live links. If you want the details, go to the links. This talk is more advertisement than details by necessity. And so this is from the CF4 report. This was really our argument that SPEC-S5 could play a key role in studying cosmic acceleration. This is showing basically the fraction of the critical density in dark energy as a function of redshift. And these shaded regions are constraints, stage 3 onto what you might have with LSST for W0 WA modes. Right? So it turns out, even with current constraints, the space of the range of values at high redshift is quite strongly constrained in these models, just by having the W0 WA parameterization. But there are many theoretical models of what dark energy could do that go outside those bounds at high redshift, but are consistent with them at low redshift. So if you really want to exclude these whole swaths of models that have in many cases been invoked to deal with tensions in the data, other sorts of tensions, we really need to constrain what is happening with dark energy at these higher redshifts. And SPEC-S5 is really the best answer to that until we have line intensity mapping working, which we don't expect to have on the same timescales. And so I'm just going to show, again, advertisements, a series of plots from the SNOMAS reports, different applications that we saw for SPEC-S5. So from CF3 on dark matter, by getting a spectroscopy of dwarf galaxies with a telescope that is identical in parameters to what you would want for SPEC-S5, you can get constraints on the mass of dark matter particles in warm dark matter scenarios. From CF4, measuring the power spectrum across a broad range of scales, SPEC-S5 is the best answer at scales we haven't been able to do well before. We heard about the primordial figure of merit, the number of linear modes that are well constrained, that we'd like to up by something like a factor of 10. SPEC-S5 is our best answer for that in the next decade or so. So the same measurements actually give you a sensitivity to early dark energy at very high redshifts. So this is not Z, but log Z on this scale. And a SPEC-S5 can set strong constraints and exclude, again, a wide breadth of scenarios. We can perform tests of primordial non-Gaussianity. We heard a lot about that. We can also get constraints on the number of light species by measuring, again, the power spectrum with high detail. So from the CF4 panel, which again was the one that focused most on SPEC-S5, we set a set of key quantitative targets that we would want this facility to be able to do. So to be able to measure dark energy out to Z of 5, where in lambda CDM or W0 WA models, the density becomes negligible. To test for signatures of non-Gaussianity well enough to exclude F and L local of 1, to constrain the number of light species at the 0.02 level. But we also had a set of goals that really are opening up new windows on the universe. So searching for primordial features in the inflationary power spectrum, testing modified gravity models at high redshift through things like redshift space distortions, measuring the sum of the neutrino masses, addressing tensions and measurements of the Hubble constant and the power spectrum amplitude. One great thing about things like this low density sample is you have multiple tracers of the large scale structure from having multiple types of galaxies with very different biasing, and also multiple tracers of the matter. You have not just the clustering of the galaxies, but you have lensing, galaxy-galaxy lensing, CMB lensing. So you really have ways to address whether there's any systematics going on. But there's also another role for SPEC-S5, which is to enhance the other flagship experiments, Rubin LSST and CMBS4. So for Rubin, a key thing that a SPEC-S5 can do that is very difficult without something like it is improving the photometric redshifts from Rubin, which can increase the figure of merit by a factor of 2 if you have optimal photoz's. Another thing it unlocks is a lot of information via cross correlations with cosmic microwave background. Not just lensing, but every sort of SZ effect people have ever talked about, on and on and on. There's an extreme wealth of information. So I just want to highlight the Rubin case because none of the other talks, I think, are. So for Rubin science, we are relying on tracers of the universe that are relatively faint. And that means they're very difficult to get spectroscopy of. And so we need to rely on photometric redshifts, on redshifts estimated from imaging alone. And we're going to something like I of magnitude of 25, which is more than a factor of 10 down from where current surveys have high redshift success rates. And so if we can get a larger sample of secure redshifts, so this is a plot that actually Rongpu Zhou, who's here, made. The errors on your photoz's get smaller and smaller the better your constraints are on the relationship between galaxy color and redshift. And the estimates are we need something like 20,000 redshifts spanning the properties of the full sample to get into near optimal results. And so this would particularly enhance not the weak lensing from Rubin, but large-scale structure measurements, where the large-scale structure maps tighten up a lot when you reduce the photo-Z measurements. And also cluster finding. It becomes a whole lot easier to find clusters as over densities when your redshift errors are smaller. And so we heard yesterday about the complementarity of measurements of the halo mass function to other probes for SPEC-S5. If you want those halo mass function measurements, galaxy clusters are generally the way to go. That gets a lot better with better photoz's. And so it turns out a SPEC-S5 is nearly optimal for obtaining them. Simultaneously, by basically trading off amongst somewhat brighter sources, you can get the spectra you need to constrain intrinsic alignment models, which is one of the major systematics in weak lensing studies. So this can greatly enhance the science from something like LSST. So one thing I wanted to comment on, we heard a definition of SPEC-S5 yesterday, which is basically something that can multiply the primordial modes by 10. I did want to mention what SPEC-S5 actually meant to snowmass. For snowmass, SPEC-S5 was really defined by its ability to do all the different science that people had laid out, looking at the galaxy halo, looking at low redshift tracers, looking at high redshift tracers simultaneously. So it's really being able to do all of this science that made something a SPEC-S5 rather than one particular measurement. Because this facility really would be tremendously flexible in many different scenarios. And P5 kind of highlighted that, right? They talked about different science goals for SPEC-S5, but also about how we need to determine the balance between those goals. Once we've seen the DESI data, once we've seen early Rubin LSST results, because it's hard to predict what 10 years from now the key science is going to be. So just a few quick conclusions. So really, there's a lot of thought went into snowmass, much of it from people in this room. I want us to not lose track of that. I want us to take advantage of that and sort of build on that further and further. That's really what our goal was in working on snowmass. So look at the CF3 report for dark matter cases, inflation, dark energy, light relics, look at CF4, and to some degree CF5 and CF6. And I want to just highlight, in line with P5, we want to make sure that we do not end up optimizing Spec S5 for one thing because we don't know the best science 10 years from now. So I do want to make sure we keep an eye on making sure it's a flexible facility to the degree possible. And finally, I just want to thank everyone who put into work on SNOMAS. These reports are made possible by the efforts of many, 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 many people across the cosmic frontier and beyond. So thank you. All right.
One quick question, urgent question, let's wait for this question. Okay. Got questions for you. Okay, next speaker is Salim. Next speaker is Salim Botinli, who is going to tell us about synergies with the cosmic microwave background.
Stop sharing. Should I figure out how to put this on? All right. Let me just use this. Speak it. All right. Yeah, thank you very much. It's great to be here. I was tasked with talking about synergies, giving a brief review on synergies with CMB. And on that, I will be talking about all these interesting effects that we will have in the CMB. I mean, we have in the CMB, such as those that are sourced by gravitational potentials, Thomson scattering, as well as other things like dust. And talk about how the cross correlations with large-scale structure surveys, in particular with Spec S5 in mind, will really help us to maximize the information content in the CMB in the context of these imprints in the near future upon cross correlation. So I'll be talking about lensing and SC effects, but there will be other talks that talk about some other such effects that follows. And I'll start with lensing. Of course, lensing, CMB lensing and large-scale structure cross-correlations. CMB lensing is a very powerful probe of the underlying dark matter structure. It's not sensitive to galaxy bias, but the CMB maps are projected maps on the line of sight. So the lensing information is projected on the line of sight. And galaxy cross-correlations really allows us to measure lensing in redshift slices and perform tomographic analysis of lensing, which of course has a very broad redshift kernel, with significant contributions from redshift 2 to 5, and the kernel peaking around 2. These upcoming surveys like Spec 5 can indeed improve the information content from CMB lensing upon cross-correlation very significantly. For example, allowing us to probe luminous matter and the relationship between the luminous matter and dark matter up to high redshifts, as well as breaking the degeneracy with the galaxy bias and probing the matter fluctuations in a way that's more robust against the details of selection functions, inhomogeneous spatially varying noise, intrinsic alignments that the galaxy weak lensing suffers, for example, as well as various other effects, including assumptions about CMB experiments. So measurements of the matter power spectrum, of course, is very useful to measure the growth of structure. So CMB lensing and galaxy cross correlations, we can measure the sigma 8 to high precision, which of course sees a suppression due to massive neutrinos. And there's a good set of recent forecasts that suggests that upcoming future large-scale structure surveys can constrain this mass of neutrinos beyond 2 sigma for a given normal hierarchy, or can make high significance suggestions of new physics, as recently been suggested. And higher redshift information up to higher redshifts will indeed improve this up to around 3 sigma, as covered and discussed in some of these papers that I link here. So this will be a very exciting probe. In addition, of course, you can do from cross correlations with CMB lensing and galaxy surveys. One can probe general relativity, for instance, this EEG parameter that provides a consistency check on GR, which is sensitive to the ratio of the Newtonian potential and the curvature potential, which the deviations from GR have predictions for that extends to higher redshifts. So with the survey like SPEC5, we can also measure this parameter to higher redshifts, putting more stringent constraints on deviations from GR. As well as, of course, primordial non-Gaussianity, as we discussed yesterday, in particular from galaxy bias, scale-dependent galaxy bias. And there's lots of work in the literature that suggests that addition of CMB lensing to galaxy surveys improve of the order of magnitude on constraints on the local non-Gaussianity upon cross-correlation with CMB lensing and large-scale structure. I will return to this later in the context of SC. But these are some of the science targets for CMB lensing galaxy cross-correlations in the future. All right. The other contribution to the CMB that is of relevance is the Siemens-Zaldosch effects, which are the inverse Compton scattering of CMB photons with free electrons in the late universe. And they probe the diffuse ionized gas. And out of these, the thermal Siemens-Zaldosch effect, which is sensitive to gas pressure, as well as the kinetic Siemens-Zaldosch effect are very relevant and valuable sources of information. And the kinetic Siemens-Zaldosch effect, of course, probes the bulk velocities of electrons and the rest frame with respect to the CMB. And they're also sensitive to the column density of the electrons. So these two effects probe, when combined, the full thermal state of gas in the universe and can be used to improve cosmological constraints as well, as I'll describe in a minute. Now, traditionally, up until now, CMB cross-correlations with large-scale structure were in particular useful for stacking TSC and KSC patches on locations of galaxies in order to assess or learn more about astrophysics. So this involves stacking CMB patches with, which could help also from knowledge of redshift information in order to measure, for example, the electron profiles or the pressure profiles, which gives us hints, for instance, about the baryonic effects in the matter power spectrum and weak lensing, which the hydrodynamical simulations have predictions for. And of course, this is very implicative for relevant cosmological parameters like sigma 8 that suffer from baryonic feedback or this gets suppressed. And then we can compare these stacks that we make out of stacking CMB patches with different hydrodynamical simulations and ultimately understand better the implications of baryonic feedback as a function of redshift. So the upcoming SPEC5 surveys will be very, very helpful for understanding, for example, potentially the sources of tensions that we see like sigma 8 in the near future. But also in the near future, the CMB, these SC effects, in particular the kinetic Siemens-Zaldosch effect, will prove to be a very, very strong probe of cosmology as well. And that's because the kinetic Siemens-Zaldosch effect depends on these radial velocities, these radial peculiar velocities that the electrons see in the rest frame, which is really a cosmological mode. It's a cosmological fluctuation. It's coherent up to 50 megaparsec scales. And what we do is essentially we devise quadratic estimators that essentially uses the fact that the CMB galaxy cross-correlations become statistically anisotropic in the presence of these large-scale velocity fluctuations, and in turn reconstruct these velocity fluctuations. So this is called the KSC tomography or velocity reconstruction, which is suggestive to be a very, very powerful probe of cosmology as well. And there are a few reasons for it. And of course, the main reason, or maybe the most standard reason, is that it provides a multi-tracer probe of large-scale structure. So it adds velocity fluctuations to the picture. And this, in principle, essentially removes the cosmic variance upon cross-correlation and allows us to constrain things like galaxy bias or the growth rate without being subject to cosmic variance. But there are other benefits too. For instance, velocity fields or the reconstruction noise for the velocity fields behaves like velocity. In other words, it's like shot noise in velocity. So when we're trying to constrain matter fluctuations from velocity reconstruction, the noise in the matter fluctuation scales with an extra scale factor squared. So that means that on largest scales, KSC velocity reconstruction does worse, but on smallest scales, KSC velocity reconstruction does worse, but on the largest scales, it actually performs much better in principle than galaxy shot noise, for instance. So this provides a very powerful probe of very, very ultra large scale deviations from lambda CDM. In the context of Spec 5, there's also a huge benefit from having redshift information on the account that these velocity modes are really radial modes. And as you measure the redshifts better, as you can see from here, comparing LSSD and Spec 5, especially on high redshifts, the velocity reconstruction noise will behave much, much better, improving the information content from the velocity reconstruction. So one of the main science targets of this program, of course, is measuring the scale-dependent galaxy bias, the local non-Gaussianity, FNL, which we've discussed yesterday in detail. And here I show the contribution to the galaxy bias from this local type of non-Gaussianity, FNL, as well as tau NL that Oliver also introduced, which can be given in terms of FNL in the single-field swirl inflation, but also deviates from this in principle if you have multiple fields with different matter power, with different corresponding power spectrum, for instance. And we have shown in various works in recent years that the KSC reconstruction in cross-correlation with the galaxy will improve the prospects of measuring these non-Gaussianities in principle very significantly. So here you see, for instance, a forecast for LSSD using the LSSD auto-power spectrum. And you can see that the FNL and tau NL constraints actually end up becoming cosmic variance limited with increasing the number of galaxies, for instance. But if you add KSC reconstructed velocities into picture, then you can actually push beyond the threshold of unity, which is, of course, a meaningful threshold in the context of these parameters. So this program has been going on, and we have many people, including at Perimeter, as well as different other places that work on this. And we have tested extensively with simulations to find that the things are under control. We understand the contributions and foregrounds to the most extent, and we're now testing with data as well. So this here you see using some marginalized posterior from the Unwise and Planck using velocity reconstruction, which are, of course, not ideal experiments to reconstruct velocities for, but I suspect this would be the first constraint plot that you'd see from actual data on this FNLs plus or minus 100, which is not very competitive with current constraints, but this will improve by orders of magnitude in the near future. And of course, this velocity reconstruction in cross-correlation with galaxies are useful for many different science targets, including probing pre-inflationary relics like evidence for eternal inflation or CMB anomalies, relativistic effects, dark energy, isocurvature, modified gravity, and many others. So you can check these reference links if you're interested. Now, the SC effects are not limited with kinetic SC or the thermal SC. There's also polarization. The CMB maps are polarized because the electrons, they see a remote local quadrupolar anisotropy in their rest frame. And this induces a polarization called the polarized SC. It's the standard polarized SC. And it, of course, depends also on the column density of electrons, as well as this quadrupole that they see in their rest frame. Now, this is a little bit more speculative in the sense that we haven't yet started testing with simulations. But nevertheless, there's some value in being excited about this signal as well, partly because the quadrupole, this remote quadrupole seen by electrons, unlike the case of KSC, is actually dominated by the primordial quadrupole, so the CMB quadrupole that these electrons see in their rest frame. So in principle, this observable probes the CMB seen by electrons all throughout the universe, so in turn extending the light cone very significantly, as explored in many works that I cite here. There are many reasons to, in my opinion, to be excited about something like this. And essentially the main reason I would argue is for possible follow-ups, for breakthrough measurements. Okay. One example, for instance, is the tomographic measurement of the birefringence by cross-correlating the PSC effect with galaxy surveys, as shown in this work by Namikawa and company, and we have also shown as well before that, which allows actually one to constrain if, for instance, the birefringence is observed, one can ultimately also constrain whether if it's dark energy-like or dark matter-like. So I can talk about that more as well. All right, finally, I want to, and of course, there's also other science goals for this, like measuring primordial tensor fluctuations because it's a spin-2 field, as well as CMB anomalies, primordial non-Gaussianity, optical depth reionization, and other science goals. All right, in the last minute that I have, I want to also propose another science target, which might not be a main science target, but I think it's a very interesting one. And it's one that SPEC5 survey can ultimately be uniquely available to constrain as well. So this is to do with the ionization of the second electron in helium, which has the ionization energy of 54 eV. So it doesn't get ionized during the ionization of hydrogen, but it ionizes when the first quasars and AGN form. And there's already experimental evidence from Lyman alpha forest measurements that this transition, which is 8% of all baryons or all electrons becoming ionized, happens around redshift 3. So you see here Lyman alpha measurements, which clearly shows a suggestion that the helium ionization, helium-2 reionization starts around redshift 4, ends around redshift 3 or 2.5. So you see here in this is essentially fitted plot to data, but the Lyman alpha measurements themselves are very model dependent. They compare the flux, Lyman alpha flux, to simulated temperature in a set series of simulated temperatures and pick the temperature essentially best matching the corresponding Lyman alpha flux power. In other words, it's actually a very model dependent measurement. So additional probes are very valuable for this epoch. And of course, this epoch itself is very exciting on the account that it, of course, probes the properties of quasars, as well as fundamental physics, like the growth of and evolution of supermassive black holes, as well as a probe of the primordial helium abundance. So it's a very exciting and so far uncharted epoch in the universe that I think is very exciting. And the properties of quasars, for instance, really impact the history of this reionization pretty significantly. So you see here with different lines, the ionization fraction reproduced by mimicking quasar abundances, spectrum, and clustering. But if you change these within the error bars of the existing experiments, we see significantly different ionization fraction or helium reionization history. And of course, CMB, in particular the SC effects, are sensitive to this ionization fraction through sensitivity to column density of electrons. And the cross-correlation between galaxies and CMB ultimately will have the power to probe this epoch to high significance. So SPEC5 survey, for instance, can put really, really stringent constraints to helium reionization. And I think this might also be worthwhile science target for a survey like this. Okay, so I'm going to stop here. Thank you very much.
Any urgent questions? Okay, we will ask questions more in the discussion section. Next speaker is Elena Pierpali, who will talk about the transverse lens, sorry, the moving lens effect. Thank you very much.
So where is the? Okay, so this doesn't move, but how do I actually connect? Oh, it's solid. And then I have to start the. How do I do it from here?
This bar for you, and if you click here, you should be present.
All right. But this is not. So good morning, everybody. So thank you very much to Selim for the nice presentation about all the wonderful physics that you could achieve by cross-correlating. I'm going to focus on one particular effect, and just because this is the one I dealt with, but in a sense, it's a little bit of a prototype of the kind of work that we would need to do in order to make these results happen. So I'll comment about that through the talk. So I'm going to talk about this moving lens effect, which essentially means if you have an object, a halo that passes across your line of sight, then the photon from the CMB that is coming to you and is passing through this potential experience a variation in a potential. So you get a sort of a ISW effect. And this ISW effect is different from the photons that are passing like behind the halo with respect to the one that are passing in front of the halo. So as a result, you get in temperature a sort of dipolar structure, and the direction of the dipole is determined by the transverse velocity of the object. And then it's relatively extended over there. There is no pointer, but like over there, you can see that it is that this is the virial radius. It's a super tiny, so this is 0.6 micro-K for those who are used to these units. So it's a very, very tiny effect, but it's present in all the halos, and it traces the velocity field. So this is very cool because it's essentially, you know, it's one of the two ways in which we can measure transverse velocities. And so you get excited, you want to try to see whether it can be detected. This effect was pointed out several years ago, but only recently it was shown that the upcoming experiments are able potentially to detect it. However, how do you actually go forward here? Oh, here. So, however, in all this business, because these are super tiny effects, there are real world challenges. First of all, there are a bunch of other emissions that have the same type of frequency dependence, so black body dependence. So even if you were given like a CMB map with just everything that emits as a black body, it would be hard to detect this effect because it's super tiny with respect to everything else. But then on top of that, you also have some other astrophysical emitters that are in your way. So you definitely need to do what we call component separation. And then if you do that, you see, you know, this is your clean map. So to speak, you still see all these points over here that are probably the KSZ and so on, and look at the overall amplitude of this map. On top of that, you know, just going forward, there are a lot of like residuals from these other effects in your map, right? So how much can you extract really from the maps when you have all those elements together? So so this is a difficult business. The detection of this moving glass hasn't occurred quite yet, and on an individual object basis, it's going to be hard. So you want to do it statistically, and we envisaged a couple of ways to do so. But then most of all, you want to base your analysis on simulations that kind of can convey all the information for all the correlated emission and so on. So we used as a baseline WebSky, which has many of those realistic effects in it. But then we also implemented some other, you introduced the moving lens effect and also the halo effect. Even if the halo doesn't move, there is some lensing that creates a dipole in the direction of the gradient of the CMB, and that can be in your way, as we will see. So in practice, what we do, you take your multi-frequency maps, and then you choose a component separation method. And this is important, like, so the choice that you make is going to influence your result pretty much. Then you take out of this component separated map, you take, you know, the map that represents a black body emission. And then we try two strategies. We did oriented stacking of the halos, and then we tried to look at pairwise velocities and to see whether this, you know, this would lead us somewhere. So these are the two configurations of experiments that we tried. So indeed, this science is possible only if you have very large overlapping region. And what we have found also is that you want to have a lot of halos in your region. And I'll comment on that later on. So in doing our exercise on the stacking, like you do see that you can see the halos in the moving lens effect very well. And you can also see it in the general maps of the black body reconstructed CMB. But what we learned is that, in fact, there are some residuals that are due to the Therma-Sunel-Zeldovich effect and the cosmic infrared background that do correlate also with the velocity of your object. So you can't ignore that, and you have to find a way to try to remove those more optimally. Those might also be another way, these are physical effects, and they might provide a different way to actually measure this transverse velocity. And the importance of them depends on the mass of the halo and also the redshift where it is. So this is potentially a new venue for this analysis. Then, so how well can you do with the stacking? This is a complex plot, but so the main things to get here is that if you pass from DAISY densities of galaxies to LSST, you gain a lot in just simple noise that you have in your map. So you do want a lot of halos to be present in your field. And then also you do have some annoyance. If you don't do anything, you just take the simple component separation approach that we adopted, you don't get a detection essentially. But if you can, if you're able to subtract better, especially the CIB and the TSZ, but also to some extent also the halo lensing, yes, then you can get a detection over the signal to noise of 5 to 10 according to what you do. So hopefully that can be done. So the other important question is, what halos do you actually need? Very small object, distant object, nearby object. So what we found in general is that the fact that you have foregrounds tends to push the halos toward mass, giving more importance to more massive halos and relatively lower redshift. Of course, this can change if you improve your component separation or if you change your experiments. The very last, the other way that we tried to detect this signal is just to look at the pairwise velocities. You're probably familiar with that because of the kinetic Sunyaev-Zeldovich effect, which is sensitive to the radial velocities. This estimator is actually based on the transverse velocity, so it would be complementary in a sense. And we did see that, like with the CMBS4 plus LSST, you can detect this signal at about 9 to 15%. Sigma of around 10 again, 9 to 15. And then most importantly, this has different systematic effects than the other detection strategy. So the fact of having the two helps in that respect. So as a summary, so yes, the optimistic results of a few years ago that didn't consider the real world are confirmed in a sense, so we will be able to detect this signal. However, in general, we do need good simulations with correlated physical effects. So we need a good estimate of the noise. For example, for CMBS4 at the scales that were of interest for us, there wasn't such a thing when we started the analysis. And also the simulations themselves, we couldn't do this kind of analysis for CMB-HD, which has a higher spatial resolution, and would have been interesting to see how much better we could have done, but the simulations were sort of not good enough, quote unquote. So we do need better simulations to be able to address all these issues. And let me add, I think in polarization, this is going to be, so we're really even behind in that respect. And then because we were asked to quote how much future surveys may help. So here you get a sort of an idea. How much you reduce your signal to noise if you remove, if you add your errors in redshift with respect to removing it, you gain a few sigma. But all of these estimates do depend strongly on your technique to detect the object, your component separation strategy, and so on. So it's actually not easy to give a really good assessment for how much a survey will do. whenever you deal with this such tiny effect. And you need detailed studies, which can be also numerically very expensive, like all this pairwise velocity business. When you have all those halos, takes up quite a bit of computational time. That's it.
Yeah, any urgent? Okay, questions, discussion, we're gonna move on. Good segue from Eleanor's closing comments. The next speaker is Julian Belts-Morma, talking about multi-rate plan.
Does that work? I use this mic? Great. Hi, thank you. My name is Jillian Belts-Morman. I am a postdoc at Argonne National Lab, and I'm going to tell you about a new model for making multi-wavelength, multi-redshift predictions for future cross-survey cosmological analyses. So I think the next decade of cosmology is going to be really exciting, especially because the next generation of cosmological surveys has the potential to uncover observational signatures of physics beyond the standard model. And in particular, I think there is a wealth of new information to be accessed by including higher order clustering statistics, clustering in the nonlinear regime, multi-redshift constraints, and cross-survey analyses. All of this new information sounds great, but if we really want to harness all of this new constraining power in a way that is robust, we need a couple of things. First, we need a flexible model of the galaxy halo connection that is accurate down to small scales if we want to push to the nonlinear regime. We also need the ability to model survey systematics in a way that is physically meaningful and sufficiently complex. And finally, we need a framework that allows us to make these multi-tracer, multi-redshift predictions simultaneously in a way that does not blow up our parameter space. So we have set out to design a new model of the galaxy halo connection to do all of those things. Our goal is that the model be based on simple physical assumptions and that it be suitable for making these multi-redshift, multi-wavelength predictions. And we have formulated our model to make predictions in a fully probabilistic and differentiable way, allowing us to leverage the good scaling of the JAX auto differentiation library on multi-GPU supercomputers. And our long-term goal with developing this pipeline is to do a full-scale, multi-redshift, multi-tracer cosmological analysis that includes data from multiple different surveys, including their cross-correlations. Because all of our predictions are formulated to be fully differentiable, we have named our pipeline diff-sky. And I don't have time in this 10-minute talk to go over all of the details of the modeling pipeline, but briefly, we have parameterizations for how halos grow, how galaxies form stars in situ, how galaxies merge, and how to predict the full SED of the galaxy, including taking into account things like dust attenuation and bursty star formation. And I want to emphasize that all of our model parameters have physical interpretations, and we are seeking the minimum interpretable parametric flexibility that is required to accurately capture the data. I would say that in the spectrum of galaxy halo connection models, diff-sky lives firmly in the empirical forward modeling regime. However, it has the flexibility and multi-wavelength predictive power of a semi-analytic model, but it is not a SAM in the sense that there are no ODEs governing the transfer of energy. We are also taking advantage of AI/ML techniques to significantly speed up our modeling pipeline, but it is not a machine learning model because all of our model parameters have real physical interpretations. And as we continue to develop our model, we can validate its flexibility using other models of galaxy formation like hydro simulations and semi-analytic models. So again, I want to emphasize that this modeling pipeline gives us a really new capability to make multi-redshift, multi-wavelength predictions simultaneously, which is really ideal for fitting different data sets from different simulations or from different surveys and for doing these cross-survey analyses. This model also allows us to model systematics in a way that is physically meaningful and complex. We are also able to provide validation data for other pipelines to test their robustness, which is really important as we continue to push toward higher order statistics and toward the nonlinear regime. And I just want to advertise quickly that we already have the ability to populate different simulations like UNIT and Abacus with galaxies from our model. So if anyone is in need of mock galaxy catalogs, let me know. I just want to illustrate briefly the current capabilities of our modeling pipeline to fit data from different surveys. So here I'm showing some fits to color distributions in the DESI BGS sample. On the left, it's BGS galaxies at redshift 0.3, and on the right at redshift 0.5. And our model are the green and blue contours. And I want to point out that although it's not shown, in addition to fitting to these color distributions, we're also fitting to number densities and satellite fractions in the BGS samples, as well as LRG number densities and satellite fractions at several different redshifts. So we already have this multi-tracer, multi-redshift capability. Just to show some fits to other surveys, on the left, we're fitting to some luminosity functions in the SDSS main galaxy sample in the R band and I band. Our model is the dashed lines. And on the right, we're fitting to some color PDFs in Cosmos data. Again, our model is the dashed lines, and on the top, we're fitting to colors at lower redshift, and in the bottom panels, we're fitting to colors around redshift 1. So again, these are just some preliminary fits to several different data sets, but I think our capabilities are already pretty encouraging and exciting. Like I've said, one of the things we can do currently with our model is make mock galaxy catalogs to use in validation tests for other pipelines. So these are often called mock challenges. And the idea is that a pipeline using a different model of the galaxy halo connection like HOD or EFT can confirm whether or not they can recover the true cosmology when our mock, which comes from a totally different model of the galaxy halo connection, is used as the true data set. And I think these mock challenges represent a really important growing trend in the field for validating the robustness of cosmological analyses as we push toward higher order statistics or nonlinear regime clustering. I am currently leading the DESI emulator mock challenge, but I also want to highlight the Beyond 2-point challenge, which was mentioned yesterday. It's just another example of a really great mock challenge that's currently happening in the field. I just want to quickly show the current state of the DESI emulator mock challenge. These are some plots made by the alternative clustering methods group within DESI, who are participating in the challenge to validate the robustness of their higher order clustering statistics. And I just wanted to show these figures to highlight the diversity of clustering measurements that are being used in this group. So in addition to correlation functions, they're using density split clustering and void galaxy cross correlations. And in each of these panels, the black dots are our mock, and the solid lines are several different HOD realizations that are being used. And these are just to show that the HOD realizations encompass the space that our mock takes up. And again, I think this is a really important push toward validating the robustness of these higher order analyses. And again, our long-term goal with developing this pipeline is to perform our own full-scale, multi-redshift, multi-tracer cosmological analysis that uses data from multiple different surveys simultaneously, including a future spectroscopic survey. So speaking of future surveys, I think in general, our modeling pipeline is really useful for supporting a wide variety of science between redshift 0 and redshift 5, and particularly for making multi-wavelength mocks that can be used for joint modeling of different surveys like LSST, DESI, Roman, and a future spectroscopic survey. In terms of our personal interests, we are interested in using this pipeline to get joint constraints on both cosmology and the galaxy halo connection using both clustering and lensing in the nonlinear regime. And we are particularly interested in targeting the growth of structure between redshift 0 and redshift 1. So for this, we would be very interested in having complete magnitude limited samples of galaxies between redshift 0 and redshift 1. And I think I'm out of time, so I'll just conclude by saying that all of this work has been done in collaboration with all of these people. And if this sounds interesting to any of you, our team at Argonne is growing. So if you're interested in collaborating with us, please contact Andrew. He's right over there. Thanks.
Thank you very much.
An urgent question.
Not that urgent. Urgent question.
Okay.
Oh, wait. Oh, there was, okay.
Nice talk. Yeah, I just give a small clarification. I mean, can you say in a couple of words what do you mean when you say that you are not using ML, but you're using ML technologies to speed up or so? I mean, you said something along those lines, and it was not clear to me what you meant.
Right. Yeah. So I mean that this is not a strictly machine learning model. It's not a neural network or anything like that. We are using JAX, which is an auto differentiation library, and our models are based on a lot of sigmoid functions, which are commonly used in machine learning models. But all of our parameters have physical interpretations. They're not, typical like neural network parameters.
Thank you very much. Next speaker will be Ian Meyer, talking about topological interpretation.
I'm on Zoom, yeah. So just share the screen. Yep, right. Yeah, good morning. I want to thank the organizers for putting together this workshop and for encouraging or challenging us to maximize the scientific return from SPECS S5 surveys. And so in that context, one strategy is what Gillian just talked about, pushing towards small scales, nonlinear regime. And another alternative route is analyzing these quasi-linear regimes where we have perturbative control, like Misha highlighted yesterday, but in a bit more optimal way. So that will be the focus of this talk, where we'll be talking about how to analyze galaxy clustering data directly at the three-dimensional fields level. This is a work in collaboration with the group at MPA, including Fabian Schmidt and Beatrice Tucci, and many other people. So the current focus of our science targets is growth of structure, because this is competition between dark energy driving the expansion and gravity attracting galaxies and amplifying the growth of structure or density fluctuations. By measuring sigma 8, so the standard deviation of matter fluctuations within spheres of roughly 8 megaparsec, we at different redshifts, we can follow the redshift evolution of sigma 8 and then hopefully gain some insights into new properties of dark energy, gravity, or any possible interactions within the dark sector. I would like to mention here also that usually consistency test for any deviation from lambda CDM is model independent, but as soon as you want to, say something concrete about these new properties, you usually need to be consistently model any extensions in some model dependent way, like Emmanuel had pointed out yesterday. And so the SA tension or sigma 8 tension is the discrepancy between measurements by the cosmic microwave background, probing the large scale and early universe, and the galaxy weak lensing, probing the small scale, but also at late times. So if of physical origin, this is indication of new physics, but we don't know for sure whether that is a difference between physics at late versus early time in the universe, or between small versus large scales. And to me, galaxy clustering provides a perfect possibility to pinpoint the origin of this tension because it probes the lazy universe, but on large to quasi-linear scales. And so as we all know, in spectroscopic survey, we have the 3D information about galaxy distribution, but usually we summarize them into like low order endpoints functions like the power spectrum or bispectrum. And so our proposal is that we skip this compression and we directly model the data at the 3D fields level. So that is to put the galaxies and your survey into a box or 3D discretized grid, and then each voxel will be a parameter, including, and then on top the cosmological parameters that we will infer. And so let me just show you upfront what is, what can we gain by analyzing the data this way. So in this paper with Fabian and Beatrice, we show that in fact, there is a several factor of improvement if you go from power spectrum plus bispectrum to field level statistics. And before I go into the details of the results, I just want to quickly highlight that this is an apple-to-apple comparison where we make sure that we use the exact same Fourier modes for both statistics. And there's no redshift-based distortion information in this comparison. So that will be a separate study. And so here I'm showing constraint on sigma 8 from power spectrum plus bispectrum in yellow and field level statistics, or we call it field level Bayesian inference, FBI. In hindsight, terrible acronym, but at the time I couldn't resist. From two separate simulations, so two separate samples of dark matter halos in n-body simulations, bias tracers of the underlying matter field. And so you can see the improvement, first the scale cut of the analysis, the Kmax that we go up to, very modest scales, 0.1 to 0.12. So, you know, scales where we have definitely perturbative control. And already at these scales, we can see the improvement factor is quite promising, going up to a factor of 5 in one case. And that would be, you know, basically increase the survey volume by factor of 25. And the improvement is quite robust across halo samples. Here I'm only showing the results from n-body halos, but in the Beyond 2-point challenge that many of us have already mentioned, you will also find results for simulated galaxies assuming HOD model. So let me just now spend a few minutes to describe what we did, what this framework is about. So it's basically combining Lagrangian perturbation theory for the gravitational evolution and EFT, field level EFT for the matter-galaxy connection. So Misha already explained everything about EFT beautifully yesterday. I just want to quickly recap that we stay on large quasi-linear scales and we do the bias expansion. The small scale physics that relevant for galaxy formation is either suppressed or marginalized over, in which case they are captured by the stochasticity in violet. And putting together these two components, we have Labs field, which is a framework to directly model the galaxy fields at the field level very efficiently, very fast. So what happens when you have a fast simulator like this? Well, you can do many things, including field level inference. So you start from a Gaussian initial conditions, and then you forward model, assume some cosmological parameters. Then you do the bias expansion, and now you can compare the model prediction for the galaxy field to the data directly at the field level again. And repeating this process many, many times, you can simultaneously constrain not only the cosmological parameters, but also the parameters that describe the initial conditions of the universe. Yeah, so what I just described is basically the top left of this diagram. The lower part is what we did for the power spectrum plus bispectrum statistics. And I just want to highlight this because you can also think of Labs field, again, as a very efficient simulator because it's analytic. So you can also do simulation-based inference with Labs field. So we learned the posterior for power spectrum plus bispectrum using Labs field data, and then we apply this posterior on n-body halos, and we show that it's also unbiased. So yeah, and so looking forward to connect Labs field to observations. Of course, we show that there's a lot of information that can be robustly extracted, even in quasi-linear regime by an apple-to-apple comparison. Again, there are many ways to set up such a comparison, and this is just one way to look at it. For spec S5, I would think higher galaxy density would definitely help, and then also more survey synergies. What I mean by more survey synergies is one can imagine you just not only you model galaxy counts, but you can also model galaxy shapes or galaxy peculiar velocity because they are own conditioned on or they own trace the same underlying matter field. Of course, there are observational effects and systematics that we have to also incorporate, and that would require many more future studies because we honestly don't know some survey systematics at the fields level just yet. Yeah, so that would be my talk. For more details, please check out these cosmology talks about the paper and also about the Beyond 2-Point collaboration paper that would be coming up on cosmology talks in a few weeks. Thank you.
Thank you for the nice talk. I was just wondering if you have some intuition, like where the information is coming from, beyond the power spectrum, the bispectrum.
Right. Yeah. So I think that's what we're trying to show. Basically, there's more information beyond the lower order endpoint functions. Whether or not it is the bulk of this information is located in the trispectrum or anything high up remains to be seen. So that would be a follow-up. Yeah.
More frivolous.
Okay.
Thank you very much.
Oops. So. Just share screen. Share screen. See work. Oh. 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 Turn. Yeah. Yeah, it works. So. Hello. Okay. So thanks everyone for having me here. So today I'm going to talk about what's basically the overview of what we have been doing in the UC Riverside. And it's basically the idea of multi-fidelity emulations. And what's the perspective in this talk is that how can we make numerical simulations like n-body simulations or hydro simulations useful for the future cosmological studies. And for the future studies, we are going to like more like nonlinear scales, small scales. And then if we really want to use the hydro simulations to do cosmologies, we are going to kind of marginalizing over all kinds of the kind of astrophysical effects from the subgrid models. These kind of things going to be pushing your simulation going to be very, very high dimension. So one question is that how can we do this in the future cosmological studies if each simulation is very expensive and we are going to push this to very high dimension. And so currently the useful way is to use the emulator approach, but emulator approach kind of requires you to have lots of simulations running in kind of hyperdimensional space. And you can imagine if you go to higher dimension, it's going to be very expensive to do it. And so one of the kind of idea we have is that how about we just use lots of cheaper simulations, like low fidelity simulations, low quality, but you can have many of them to fill out the hyperparameter space. And we use a few of the kind of higher fidelity simulations to kind of correct resolutions. So this idea is like you have another kind of machine learning model to help you to upscale the resolutions from the low fidelity simulation to the high resolution simulations. And one analogy is that in the university,
we have professors, they are accurate, but they are expensive to hire, so you can only hire a few of them. But you can have great student labors, they are many of them, they are inaccurate, but they are inexpensive to hire, so you can hire many of them to explore different kind of topics in the astronomy or cosmologies and use a few professors to advise them. So in this way, the university admin can maximize the not maximize the cost, sorry, minimize the cost and maximize the accuracy of the research. So putting this idea to what we have been doing in the cosmological simulations. So these kind of illustrations that you can imagine, you can have lots of like low fidelity simulations. So it's affordable to run many of them to fill out the parameter space. And you only run a few of them to kind of correct resolutions in a cosmological dependent way. And pushing this idea to what we have been doing in the Lemma forest is that we can run a suite of hydro simulations actually can cover both cosmology and the actual physical parameters we vary, including the kind of hydrogen realizations and also helium realization parameters. And also we vary the edge and feedback parameters. And all of these putting into the simulations like in 9 dimensions, and we run 50 of them in low resolutions and 3 of them in high resolutions to study the Lemma forest. In this case, we already have like 2 papers on the power spectrum. Lemma forest 1D power spectrum, and we are going to push it to like 3D power spectrum in the future. Little video I can skip. So one thing we have been doing is that running very large suites of embodied simulations. It's going to be in 11 dimension, and it's like the current 8-dimension parameter space plus the 3 additional beyond SDM parameters. It's still running, and we haven't quite finished it yet. But the idea is that pushing the multiplicativity idea to a little bit farther. That we have 2 different low fidelity nodes, one in large box, low resolutions, and one in smaller box, high resolutions, and combining both of the information and trying to predict the large box and high resolution simulations. And so it's kind of the overview of what we have been doing in UC Riverside. And I just summarize here and happy to take questions.
Are there any questions? Okay, so for the discussion, should we have a question?
So how do you actually assess how good your simulations are and for which applications you can apply them?
So the idea is that to do the cross validations, but for this case that we run, for example, a smaller box size first, that's the cheaper simulations first, and then trying to see that this framework can actually capture the resolution correction in a smaller box size. And then we run the high resolution runs, and then to validate with the prediction from the emulator using different on-trend simulation, like text simulations, we run in different parameters.
Any further questions? Okay, why don't we have the speakers come to the front? All the speakers in the session, and we can field more questions, have more discussion, and I have a few questions as well. I think we're going to get a few more chairs. You'd stand? Okay. So I thought I would start. I have a few questions that I had for the speakers. So for Jeff, I had a question about, you said something about spectra and intrinsic alignments in VRO, and it went by quickly, and I didn't understand how spectra can help out with the
Yeah, so in particular, we need models of the intrinsic alignment effects and their dependence on things like galaxy intrinsic properties to be able to predict and remove the effect from weak lensing analysis. And so those models exist, but they have a lot of free parameters. And you really need to know whether galaxies are physically close to each other to constrain those models, and you need spectra for that. Photoz's are not enough for that. And so the estimate is we want of order 100,000 objects for Rubin, not going to the full depth of the lensing samples because presumably you can test the models,
I see you're
not going quite as
take
fast.
some subset of VRO galaxies.
Right.
And then we'll just use DESI.
To get
data
spectra, to get the 3D
Okay,
information that you
okay.
need to constrain the models.
Okay, that's cool. Okay. Thank you. See, Jillian, I had a question about your talk. So you talked about automatic differentiation. And if I understand you have these simulations where you've got cosmological parameters and then you do simulations, but then you also have all this physics that involves the galaxies and the IGM and feedback, presumably. And then when you do the automatic differentiation, do you do it on a given realization of a primordial density field, or do you do multiple, do you do two different simulations with different initial conditions?
Does that work? Okay. Right. So the idea of the predictions all being formulated differentiably in JAX is really to lend itself toward running a Hamiltonian Monte Carlo eventually, because we have the exact gradients, right, through the auto differentiation. In terms of getting cosmological constraints, we would probably do that using a technique like cosmological evidence modeling, which is Johannes Lange's cosmological technique. So not quite an emulator, but yeah, the idea is to have multiple different simulations with different cosmologies and then use the evidence modeling to get constraints.
Okay.
So that sort of answered the question. So that part is a little bit different from the having the exact gradients for the galaxy halo connection model parameters.
Okay. Thank you. I had a few more questions, but I thought I'd see. Any comments from the audience? Questions? Do you have questions for each other? Okay, I had another question. Here's for Elena. So the moving lens effect, you can measure a transverse velocity. With a KSC tomography, you measure a velocity along the line of sight. So how possible is it to do three-dimensional velocity reconstruction?
I mean, that would be the final goal, but it's so with the moving lens itself, you have to see for how many halos you can actually get the transverse velocity and how well you do it. But short of that, you can probably like try to make some addition to whatever you learn. Of course, the radial velocity is much easier to measure. So most of the information will come from it, but you can try to build in some extras that you get from the transverse velocity. If you do get to measure it, then there is also the possibility of using polarization to get the transverse velocity, but that has not been investigated quite yet. And because it's hard essentially. So I don't yet have a definite answer, but of course it would be great, right? So if you could have like even some information on transverse, I don't know of any other method that doesn't come from the CMB that allows you to do that on cosmological scale. So it's hard, but it's exciting for that reason, I think.
Okay, thank you. Man, I had a question for you. The field level statistics. Have you applied those to DESI's data?
No, not yet. For now, it's
other-
only n-body simulations or HUD catalogs. We still in the process of implementing these observational effects, like I mentioned, like ISD, and then survey mask will also be a bit of a challenge, I would say. But yeah.
Okay. I have a general purpose question for all of you. So we hear about all the things that need to be done. There's been a lot of discussion about new ideas for Spec S5. I'm curious to know what kind of straightforward but really difficult calculations do you think need to be done, but people are not yet doing? Jeff, start with you.
Yeah, I'm still thinking, so I'll pass.
Salim?
I'm still thinking as well.
Um,
Wing it. Go for it.
From my perspective, so I'm someone running hydro simulation, so I'm thinking whether or not someone has been doing like if you can make the hydro simulation directly differentiable, that kind of things. But not sure it's possible or not. But if there's someone doing that, it would be great. Yeah.
Good.
Yeah, I mean, for me, it would be the same. I think there's definitely value in pushing for differentiable forward modeling. That would be useful for many approaches. And I think it would be nice to have like a consistent framework where you can combine all of these multi-traces.
I guess this is an answer that's specific to us, but I think we are pushing toward getting cosmological forecasts using our pipeline, and I think that would be a really nice calculation to do for a future spectroscopic survey, particularly including like nonlinear regime clustering or higher order clustering.
So you mean like analytical calculation or?
Any kind of calculation that's straight. So let me give you an example. Just a few years before Planck launched, CMB codes did not have a sufficiently precise calculation of the recombination history that could be done quickly.
A
And
combination
that
of
actually became available, 1 to 2 years before Planck.
a calculation of what pattern?
Of the recombination history. The uncertainties in the recombination history were larger than the statistical errors that you would have expected in Planck. So had Planck gotten their data 3 years earlier, the science returns would have been limited by our inability to model the recombination history efficiently.
But so overall, again, I think that one main thing that is lacking is that like the CMB surveys have been targeting polarization, right, for the B modes, and so there has been a lot of focus on the large scale. The small scale is complicated, and nobody looked at it. And even in order to assess how well you can do in extracting like the most prominent signals, say probably the primordial quadruple signature, you need to have an assessment of all the others, but it's not so fast and easy. And then there is maybe some theoretical work that needs to be at least revised with respect to the polarization effects in halos, I think, including the moving lens, by the way.
Thank you. So I had a question for the room. So Salim and Elena talked about really cool things that you could do by combining a galaxy survey with a CMB. And I think that this is extremely promising. And I'm wondering what is DESI going to overlap with in terms of CMB surveys? And is there coordination? And has there been thought put into how to optimize the science return from a combination of both?
Yes, I'm just looking for Simone.
Yeah.
But while we're waiting to find it, I guess I'll say that the DESI survey wasn't originally really designed with that in mind. It's mostly the northern hemisphere just because of the location of the telescope. But we're asking for an extension on DESI right now of a couple years where we would push primarily, well, exclusively further south down to declinations of at least minus 30 degrees. And then that gives quite a large overlap with, any of the Chilean CMB experiments. Yep.
So we also have an agreement with ACT that we put in place maybe 2 or 3 years ago, where we listed out several different synergies and science drivers for overlap, for science that can be derived from the overlapping areas between ACT and DESI. It ranges from kinetic SE to cross correlations in the lensing signal, et cetera. And that's, Simone is actually one of the people that really pushed that agreement and that plan. We're just starting to see some results on paper right now. I would expect to see something published in the future. We haven't produced as much by now as I'd hoped, but the overlap is significant in the equatorial region. You like plan the footprint? Does someone else want to? I just wanted to echo the strong science case.
Sorry, I'm just going to ask you that we're waiting for the microphone so anyone following online can actually hear what's going on.
All I was doing was echoing Mark's strong interest in cross correlations with missions in the South, which includes CMB missions, but also includes overlap with LSST. I'm curious to hear about other plans in which, other ways in which that science interest might inform Spec S5 planning.
Yes, I'll just respond quickly for Spec S5. The plan is we have these 2 hemisphere telescopes, and then with that, there's the flexibility to, point as you will. So as far as the southern hemisphere, obviously the southern site can see anywhere in the southern hemisphere. The northern hemisphere, as we're showing with DESI, can go as far south as minus 30. This kind of baseline plan, which is just really a placeholder right now, the high redshift survey is, just about a quarter of the sky. If there were no other information, the easiest to do would be right around the equator, but that doesn't have to be. I mean, we'd have the flexibility right up until when we start. And I will say for more near term is DESI 2, which would be starting in a few years using the DESI instrument, will kind of be a pilot of this high redshift. We actually start the imaging for the targeting for that in 3 weeks. We haven't actually decided yet exactly where we're surveying. So, now's a good time for input. In the next few weeks would be good.
So I mean, from the slides I showed, the overlap between DESI and SO as of now is like 20% of the sky. So clearly that can be improved. But also I wanted to advertise, I also put up the paper. When we were asking this question, there were no other resource than emailing poor Simone. So there is a GitHub code for computing that, and then as the Galaxy surveys evolve and so on, it would be nice just to update it so that the community can use it rather than reinventing the wheel.
I just want to add that it's important to keep in mind for the South also that roaming data well before the Spec S5 could be a powerful concept.
Thank you. I just wanted to add that on top of that, everything that Swin said, that any searches for B modes from the Atacama will probably benefit quite a lot from external tracers for delensing. So that'll be mostly photometric galaxy surveys, but the spectroscopic calibration would be very useful. So for delensing SOB modes, we'll probably be using DESI legacy survey imaging, at least for the early SAT data and stuff. Basically, the internal reconstructions are not deep enough to give you all the lenses that you need, and you would use galaxies for that.
I wanted to say the KSC tomography. So I learned a lot about KSC tomography from Salim, and I've gotten converted. It's going to be a really powerful probe. So in particular with KSC tomography, you can measure the peculiar velocity field, the large-scale peculiar velocity field, which traces the dark matter field independent of the galaxies themselves. And so usually with a galaxy survey, you use galaxies and assume they trace the mass. Here you can actually measure the mass distribution independently. And then there's all kinds of cosmological models that you can check. And one that is a favorite of mine, which is kind of a hokey model, is compensate isocurvature perturbations. So if you have a perturbation where the dark matter density becomes high, but the baryon density becomes low to compensate, so the total matter perturbation is constant, it has almost no effect on the cosmic microwave background. But in a recent paper led by Neha Anil Kumar, and Salim was involved, we showed that KSC tomography is the killer app for probing these models. You can actually probe the sensitivity to these parameter spaces by 5 orders of magnitude over what we have now with galaxy surveys at CMB. So it's a really powerful new way to do large scale structure. The other thing I was going to close with comment about some of the talks I've heard a lot about how Spec S5 is going to improve the constraints to all kinds of things. Improve the constraints to axion models, improve the constraints to dark matter models, improve the constraints to exotic neutrino parameters, improve the constraints to FNL. I always get turned off when I hear advertisements for projects. They're going to spend millions and millions of dollars to show us that a number that we think is going to be zero is in fact zero. I prefer to just reword it as opening the discovery space. It's just no big deal, but I think it just sounds better. To have a project that has a chance to discover all these exciting things rather than just show us that all these things are in fact not there. Unless there are any further comments, I think we're up. Time is up. So thank you very much to all the speakers.
Please note that tomorrow at the same time, we'll head down for a group picture for this workshop, if you're still around.